I'm here to talk about Mongo. Unfortunately, I'm kind of a Postgres fan, so this took a bit of getting my head around. So, I've been using Postgres for about 6 years, and I love every minute of it. I know exactly how to use it, I know all the problems with it, I can work around them. Postgres and me just kind of get on really well. And then a few months ago, I started a new company. I was reading the README for how to install the development environment, and I think step 2 was brew install MongoDB. And it was just kind of, oh no, really? So I fairly much convinced myself that I would come and save this company. I would persuade them to change to Postgres. I'm kind of glad I didn't, because as the time's gone on, I've realized, maybe there's more to this Mongo thing than I thought. And at the point I am today, I can probably get away with saying that I kind of love MongoDB too. Now, I don't know how much you guys know about databases. These are two very different beasts. In theory, they solve the same problem. They let you store data. In practice, they let you do it in such different ways that the trade-offs are very different. The way you design solutions with them are very different. I'm not going to do a performance comparison or a fight. They're both good tools. If you use them well, you'll get a good result. If you use them badly, you won't. I don't think one's faster than the other. It really depends on how you design your database schemas. So what are the high-level differences? MongoDB, it's a document database. This means you put basically a big blob of JSON in there, and it goes, sure, fine, I'll take that big blob of JSON, and I'll give it you back when you want it. Postgres is a SQL database, and that means its primitive is not documents, but records. So each record in a SQL database has the same structure. It's very formal. It's not like JSON where you can just have arbitrary keys and values. It's top-level columns. Every column has the same structure, or every row has the same structure and the same number of columns throughout. And although that seems like kind of a superficial difference, the philosophy behind these two formats is actually pretty deeply ingrained in the two. So with documents, you have this nice flexibility. You can just stuff anything in there, and Mongo will give it you back when you ask for it. With Postgres, on the other hand, you can't just stuff anything in there. And this is by design. It wants you to make sure that anything in your database is actually valid. Make sure it's correct data, make sure it's valid data. And it will go out of its way to tell you when you're making mistakes with things like that. And then a slightly kind of more important difference from an operability point of view is MongoDB optimizes to be available. So by default, MongoDB, you set it up in replica sets. If one of your servers goes down, it will just switch over, and the other one will be promoted to master. That means that even if you have massive server crashes, your app won't even notice. It will just keep going. Postgres, on the other hand, says, I can't deal with situations like that. If one of your databases has gone down, you should know about that. And so it protects the consistency of your data and the accuracy of everything you've written to it at the expense of, if something goes wrong, Postgres will just say, hey, something's crashed. You better deal with it. And so for the rest of this talk, I'm just going to kind of go a bit deeper into these comparisons, see what the trade-offs are, and why you might want to use one over the other. So a document in MongoDB looks kind of like JSON. I assume everyone here is familiar with JSON. You have arbitrary keys and values. So here I have a user record. So let's say I have a small website that lets you authenticate using OAuth or OAuth2 to various different social media networks. You might have a user record that looks like this. So it has a name field, which is my name, and then it has my Facebook credentials and my LinkedIn credentials. You'll notice that Facebook only needs one credential, LinkedIn needs 2. That's because Facebook's OAuth2 and LinkedIn's OAuth1. But they're basically the same. James here is just like me, except he's connected Twitter instead of LinkedIn. Twitter's also OAuth1, so that's the same structure. And you can see that there are small differences between these documents, but they basically look the same. If I want to store information about users, I'll just put them all in this JSON document, however how, and Mongo will let me look them up by that ID at the top or by searching by name. If I wanted to represent the same data in Postgres, however, it looks a bit different. So because I can only have tables where each row has the same structure in Postgres, it doesn't make sense to try and put everything into one table, because I'm going to end up with hundreds and hundreds of columns for fields that I'm not really using, like Facebook access key, Twitter access key, LinkedIn access key, all the way across. And so what I do instead is kind of transform the data by flipping it sideways. I still have the users table, which contains the information that is only about users, but then I've factored out some of this information about accounts, so it's not just dumped in the JSON anymore, it's actually structured and properly laid out. So I know for each account, these are the access key and access secret. You can see the constraints beginning to pop in here, because even though for Facebook I don't need this access secret, I still have to have a column. And so SQL databases allow you to put a special null value in there that just says, there is no value here, and I'm telling you explicitly that there's no value here. Otherwise, Postgres is going to say, when I try and insert, hey, you missed out this column. So the difference, with records, you end up with lots and lots of small things. Because every table has to have a set structure, you end up normalizing your data out, so you have lots of different tables that all collaborate together to build one thing. So when I'm requesting a user from the database, it's likely that I'm going to have to pick up 4 or 5 tables just to get their accounts, get their addresses, and just merge them all into one big object. With Mongo, it says, well, if you're going to be doing that anyway, why don't you just store the entire user as one blob? And you can just stuff anything in there, you can put any data you like in there, and you get the nice JSON properties where you can see what's there. With records, each table has to be the same, the structure has to be the same throughout, and with documents, you can have different structure per document. And this difference actually leads to kind of implementation differences in the databases. So PostgreSQL has lots of explicit support for locking and transactions, which allow you to get atomic access to lots of data at the same time. So if you want to update a user, you might have to delete 3 rows from the accounts table and update some address rows. Postgres has all this complicated SQL stuff, so you can lock different rows, you can have isolated transactions, it can update several tables at the same time. MongoDB says, well, there's no point in doing that. Just store all of your data together, and then you can atomically update one document at a time. And this is kind of good because it's a way simpler model to understand. You're not going to get yourself confused with hundreds of locks all interacting with each other. You'll either update one document or you won't. From a performance point of view, these decisions have kind of a big impact. Postgres, because every row in a table has the same structure, doesn't need to repeat the information about how the structure of the record is on every row. So it takes up less space to store data in Postgres. You can have one row after the other, they all pack together very nicely, and that space is basically all your data. There's no extra data in there. With Mongo, you have a bit more overhead, there's more data there because it has to store the structure of the JSON document every time. But because everything's at the same place, you only have to look in one place on your disk to find out all the information you need. And so as an aside, this is kind of low level. It turns out that for disks, actually the space used isn't the most important factor. It's the number of times you need to seek. So hard disks, still most people are using spinny hard disks in production. If you want to read from it, you have to wait until the disk has gone all the way around to wherever your data happens to be. I did some measurements, and it looks like it takes about 2 milliseconds to do a disk seek. This is on Amazon's Elastic Block Storage. That's a really long time. If you want your web requests to be fast, then they should be coming back in under 50 milliseconds. So if 2 of those is just waiting for a disk to spin, you're wasting a lot of that time. Once you've spun the disk, it's pretty fast to read. You can read 60 megabytes a second. No web request is going to need to read nearly that much data. So let's say with Mongo, I'm reading a reasonably chunky document off disk, so it's about 8K of JSON. It's still only 1 disk seek time, so it's 2 milliseconds, and then it's like 0.1 of a millisecond to read the data. The transfer speed is totally dominated by the seek time. And with Postgres, I have the opposite problem. Because I'm trying to read from both the users table and the accounts table, I might have to wait for the disk to spin twice in order to get the data I need. That's 4 extra milliseconds there, which is kind of slow. The reason that the Postgres solution isn't totally a terrible bad idea is that most of the time all of your data should be in RAM anyway. If you're having to wait for disks, everything's slow. And also, because Postgres has all the support for reading from multiple places, if you do a Postgres query, that's 1 network round trip. If you do a Mongo query and it turns out you do actually need more than 1 document, then you have to make 2 separate queries. And that's 2 network round trips. And if you look at EC2, you'll see that network round trip time is about the same as disk seek time. So it will quite easily get to the point where, because you're making more queries with Mongo, it's going to be slower than Postgres hitting disk many times. The actual overhead on each row, Postgres is about 24 bytes per row. MongoDB, it's n bytes, where n is the size of your JSON keys. So one of the performance optimizations Mongo people recommend is make sure your documents have short keys so that you're not wasting space on this. Both have a little bit of per database overhead or per table overhead, but it's basically negligible once you get to any number of rows. So you have these documents in Mongo that are very flexible. You can literally put anything in there. And in Postgres, you have these records, and they can only match the schema. This is a kind of hard trade-off. With Mongo, it's great. You can just write anything. So when you deploy code change, you can just start using the database immediately. With Postgres, if you want to change what's in your database, you have to run an explicit migration. So in order to write new kinds of data into Postgres, you first have to say, this is what I'm about to write to you. Can you update the schema and see why? And this sounds like the obvious worst point until you think about it from the other point of view, which is kind of the integrity point of view. With Mongo, you can write anything there. It's not going to protect you if you have a bug in your code that's writing nonsense. You have to be careful when you read out of Mongo that what you read out actually makes sense. With Postgres, you know that all these tables have the same structure, you know it has constraints, you know that the data you read is going to be totally valid. Which of those makes more sense? Well, it's kind of up to you. If you're changing your application code a lot, then maybe it's good to go with Mongo because it lets you just change the code, and immediately you can start using the database. If you're really worried that, application programmers, they make mistakes all the time, I make mistakes all the time, wouldn't it be nice if the database could catch those and make sure that we're not writing rubbish into there? It's kind of annoying that you can't get a bit of both. So in MongoDB, there's no way of saying, hey, all documents in this collection are going to have the same structure. And in the same way, in Postgres, there's not really a way of saying, well, I don't care about this so much. Though we'll have a look in a minute about how you can do something similar to that. So for real-world examples, I've seen the social network connections. In Mongo, it's really easy. I can just dump them into the JSON. And even though they're all slightly different, it doesn't matter at all. In Postgres, they're all slightly different, but I don't want to make a table for each one, because if I'm trying to join across 10 different tables, one for Facebook, Twitter, LinkedIn, Pinterest, all of them, then I might be doing many, many, many disk seeks for every query. So I want some way of optimizing this. And this is when we actually go about and reinvent Mongo in Postgres. So this is the schema we actually used to use at Reportive. And you'll see that it mostly looks like a database table, except we have this properties JSON in there. And that's just a, hey, can we stuff random stuff in here, and we'll format it like JSON. And then when we read it out, we'll treat it basically like a Mongo document. So that was kind of cool, but we lost a whole load of things that Postgres would otherwise give us, like typo correction on key names and stuff like that. And because it's one massive blob of string, Postgres is having to ship that around even if we only want little bits of it. In Mongo, we've seen the solution. It just already looks like this. So from the other point of view, what does it look like if you have a hard constraint on integrity? You want to know that your data is in the right format. So one example that I've had experience with is you've got a table of users, and at sign-up time, you collected their full name. So you have like Conrad Irwin as a full thing. But now you've decided that you want to actually call people by their first name because it's more friendly. To a first approximation, you can just kind of split on space and use the first half, but that doesn't always work. So what we've started doing is asking users for their first name and last name separately, and then we just address them by the first name. If we're using Mongo, well, this is pretty easy. We just use their first name, and if it's blank or nil, we use the name split by space and the first half of it. So, I mean, that works, but the problem is every single time I want to use the first name property on a user, I have to remember that it didn't always exist and that it might be nil. And so this is going to be scattered throughout my application unless I do something clever. And it turns out a lot of Mongo ODMs, which is Object Document Mapper, have some kind of facility for this. So MongoSkin is one of the ones we use for Node. It lets you define these functions that wrap your database. So here I'm defining a fetch function on the users collection that takes an email address. It finds one user by email, because users have unique email addresses. And then if the user has a name, but not a first name, we set the first name to what it should be. And this is kind of better, because now I only have to remember to do this in one place. And this function can just grow, and because it's all encapsulated away, I don't have to care. So if I do a bit of setup like this, then I can get back some of the advantages of knowing that all users have a first name without having to remember to do it at every point in the code. How do we do this kind of stuff in Postgres? Well, because we have this explicit migration step, when we deploy the change to Postgres that says, OK, we're not going to be collecting names anymore. Instead, we're collecting first names and last names. We just say, can you backfill all of the users that we already have and just put that default in the column? And so this will tell Postgres to split the name on space and use the first part, just as we were doing in JavaScript manually. And because we only have to run this once at migration time, as soon as we've done that, we can throw away the code. So this kind of keeps that change isolated in time. Once it's done, we don't have to remember it. We don't have to think about it ever again. So that's kind of documents and records and flexibility and integrity and the high-level structure that your application is interacting with. What about the operability side of things? So along with Postgres' idea of integrity is its idea of consistency. If you write data to me and I've told you I've written it, I'm going to assure for you that it's valid data, that I've definitely written it. It's not going to randomly go away at some point, and that whenever you ask for that data back, you're going to get it. About the only thing that Postgres can't deal with is catastrophic disk failure, but everyone uses RAID arrays for their database, so that doesn't matter too much in practice. MongoDB, by default, has a slightly different philosophy. Written means written, but if something goes wrong in Mongoland, that guarantee is weakened strongly. So if a server crashes, or if you have a network outage, and again a disk failure, Mongo can actually throw away writes. This is only by default. You can configure it to be more like Postgres, and in fact, you can also configure Postgres to be the other way around. You can configure Postgres not to consistently write to disk, and that makes it a bit faster. You can configure Mongo not to randomly throw away writes. It just makes it a bit slower. But I think most people tend to use databases as they're designed, which is in the default configuration. So the reason that Mongo does this, that it doesn't guarantee that writes remain written forever, is so that the MongoDB server can appear to be up, even if it's crashed. So most times you'll set your databases up with a master database and a slave database. The master is where writes go. You read from both the master and the slave. And having two means that if one goes wrong, you have another one ready to take over. If PostgreSQL master goes down, everything stops. It says, hey, we have a problem. You need to fix it. And that tends to mean that your app goes down. The master server is not available. Your app can't connect to it. Users are just going to see exceptions because there's no data there anymore. But Mongo has a different approach. So if your master dies, OK, we might have lost some writes that happened just before it died, but we'll promote one of the slaves from this replica set, and we'll rebalance everything. And so your app can continue writing to Mongo, and they'll transparently go to a different slave. OK, you might have lost a few writes that went to the master in that period between the master going down and the slave coming up, but your app's not going to notice. Your users are still going to see it working, and it's going to be as though nothing has gone wrong, assuming that that data wasn't essential to everything you do. This trade-off is actually a formal trade-off, so there are a lot of people working around the CAP theorem at the moment. The CAP theorem just says you can't be consistent and available and partition tolerant. So both Mongo and Postgres can cope with the network going away, like they don't corrupt data if that happens. But Postgres says we're going to maintain consistency as much as possible. Mongo says we're going to maintain availability as much as possible. Which is better? It kind of depends. So I find the Postgres model easier to understand. Either it works and it works, or it doesn't and it doesn't. But the MongoDB solution kind of does what you want magically. Because your app stays up, you're not going to have any user-facing downtime just because your database went away. You can work around this. So for Postgres, you could design a solution that causes your app to automatically fail over to a slave when the master goes down. For MongoDB, you could have some kind of write lock or write log that makes sure you never lose any data. But it's going to be a whole load of work, and you're going to end up with a solution very similar to the other database. So with PostgreSQL, it's very unlikely you'll be able to write a solution that gives you total availability and also doesn't throw away any writes. With MongoDB, the chances are you're not going to be able to write a solution that fixes this problem completely. So you kind of have this trade-off here of which do you prefer? Something that you can understand, something that if it says it's written data, has written data. Or do you prefer something that's kind of harder to understand, kind of magic? So MongoDB will sometimes just change master-slave almost at random. We've seen this a few times on EC2 where there's network interrupts for a few seconds. Mongo goes, oh my goodness, the master's gone away. What do I do? And it fails over, which causes us lost data, even though there wasn't actually a problem going on. With Postgres, I've never seen it just randomly crash when nothing was wrong. If it crashes for a reason. So that kind of ease of understanding this is pretty useful, I think. Both of these databases are very similar under the hood. So they have all these trade-offs. You have documents, you have flexible documents and availability, or you have very strict integral records, and you have the consistency stuff. But they both have the same problem, which is that RAM is really, really fast and disks are really, really slow. So for the first few months of using any database, it's going to be lightning fast. MongoDB is fast, Postgres is fast, because they never have to hit disk at all. Anything you do just comes straight out of the cache where everything is stored in RAM. It can pretty much immediately reply and send the data back to your app. And as RAM fills up, things begin to get slower. But because both actually use very similar structures underneath, they get slower in very similar ways. So both databases are built with B-tree indexes and then data stored in tables on disk. So the way a query will typically be processed is it will come into the query engine, they'll run the query on it, they'll say, okay, I have an index, so I can find users using email address really fast. I don't need to scan over the entire table, and then I can read stuff off the table once I know exactly where that record is. With Mongo, it will always hit the one document. With Postgres, it might have several different indexes and be doing some crazy complicated join across them so that it can find all the records you need and all of the tables you need in no time at all. And SQL query parsers are really, really scary. The Mongo one is much less scary. But you have this problem of everyone's data grows. Linus actually says that that's his law, is that data is always getting bigger. And so eventually, it's going to fall out of RAM. You can't pay for terabytes and terabytes of RAM. You can very easily pay for terabytes of disk. And so where most people end up running databases is not with everything in RAM, but just with what's called the working set in RAM. So the working set is loosely all the data you need to serve most of the queries. And it's normally a percentage of your data. So maybe it's the most recent 5% of your data is the working set. Or maybe you're unlucky and it's about 50% of your data. However, however much percent it is, you really want that stuff to be in RAM, because that's the stuff that's being queried over and over and over again. It kind of doesn't matter that you have to hit disk for queries that aren't in your working set, because no one's making very many of those queries, and so if they're a bit slower, well, that's fine. If you're really, really unlucky, though, your working set's going to be a large proportion of your data. So at Reportive, we had a problem where about 80% of our data was the working set, and we had about 400 gigs of data. There's no way of fitting 300 gigs in RAM without spending a fortune on Amazon bills. And so what we tried very hard to ensure was that the indexes were in RAM, even though the data wasn't. That meant that every query is only hitting disk at most once, just for that final bit at the end where it's having to read the document, not for each scan through the index. That's not very good, and most people will recommend that you don't try to run your database like that, just because disks are really slow, they're kind of unreliable, and if you're abusing them in that way, they don't last very well. So once you have this problem of, okay, you've run out of RAM, you want to make things faster, there are basically three things you can do. You can either use a bigger database, you can copy your data around, or you can split your data up and then move different bits of it to different places. So sharding is very commonly used. Using a bigger database server is less common now, but used to be very common. And replication is kind of not really on this slide for the right reason, but I'll discuss that in a minute. So using a bigger database server is something that Postgres and a lot of SQL databases actually deal with really well. So there are benchmarks on the PostgreSQL site of Postgres running on a server with 64 cores, and there are anecdotes of people running it with a terabyte of RAM installed, which is just an unimaginably huge machine. But using a bigger server doesn't work at all well for Mongo. Why? Because it still has per database write locks. I think in the next version they're making it per collection, but still the write locks it takes are really huge, which means it can only do one write at a time. So using a big server is only going to get you so far with Mongo. It's also kind of expensive. So I did some reading because I thought, wow, a terabyte of RAM sounds kind of cool. And a terabyte of RAM costs about $50,000. If you compare that to 100 gigs, which is about $10,000, that's more than 10 times the price for 10 times the RAM. You also can't do this in the cloud. Why not? Because Amazon has hundreds and hundreds of small instances and only very few of the larger ones. And the most RAM you can get there is about 200 gigs. So much more common, this works with Postgres and Mongo, though obviously Mongo much better, is to shard your data. So what you do is you take your data, split it up into evenly sized chunks, and then put those on different machines. This is great because you've basically added more RAM, which is a multiple of the number of machines. So if I have 10 machines, I have 10 times more RAM. So my working set can be that much larger before it begins to hit disk. MongoDB embraces this as the one true way of scaling. So it has this idea of MongoS's. You can shard implicitly, query MongoS. It will pretend it's a MongoD server, but it will aggregate queries from multiple machines and send them back to you. It's not great for Postgres, however. So because Mongo has this thing where all the data you need for one query is in one document, it's really easy to shard. You just say, OK, all the documents that look like this are going to be on this server. All the documents that look like that are going to be on that server. And all of the data that it needs for every query is going to be in one server, guaranteed. But if you think back to how Postgres works, you have this thing where one user, in a logical sense, might be split across several tables. So if you want to shard Postgres, you have to make sure that not only is the user from the users table on the right shard, but also the accounts table has the right bits of it on the same shard as the right bits of the user table, and whatever other tables you need are also sharded in the right way. This can be pretty hard to work out, and some domains make it, like some problem domains, you almost can't do this. It's also maybe cheaper. 10 servers that are the same cost about 10 times as much as one server that's the same. You might even get cheaper because of the bulk discounts, and it works really well in the cloud. If you have an EC2 account, you can just boot up 100 of these things, and it works fine. I mentioned replication, but it's not actually a particularly good way of scaling. It doesn't really help with write throughput, because if you're replicating, you normally have one master server that copies all the writes to slaves. So again, you're going to hit a write bottleneck. You'll hit one in Mongo. You'll hit one in Postgres. And it also doesn't really help with RAM, because if you have the same data on both servers, the same stuff is going to be loaded into RAM. You can work around that a little bit by just cleverly moving some reads to one server and some reads to another. But at that point, you're reinventing your own sharding scheme that becomes complicated again. The one thing replication does give you, which is useful if you're trying to run in this state where only your working set is in RAM, and it's a reasonably small working set, but you have vast amounts of other data. If you have your data replicated across multiple machines, you have more disks. This means you don't have to wait for less time for things to spin, because you're waiting on fewer other queries to be served from the disks. The disks will appear to be faster, just because you can read from them in more parallel. The main reason that people use replication, though, is not for scaling, it's for failover. If you have a database that has broken, and you already have another database that has exactly the same data in it, then you can trivially switch over to that database. So replication is mainly used for faster failover, not for scaling. So kind of in conclusion, I love both of these tools. There was a story I also wanted to share with you before we finished, which was set in India a while back. So there's an old water carrier, because India is very dry. They have a palace like half a mile away from the river, and he spends all day, every day, walking back and forth, carrying 2 water pots. And one day, the water pot on his right shoulder looks over at the water pot on his left shoulder and says, "You seem to have